How are you doing? We have a few minutes before the session starts. Let me check my volume here. So we will work on our assignment this week, and then going through the notes for today. And then for the lab this week on Thursday, we are going to do fast multiplication with bit shifting. So let's download the notes, and then the assignment, we'll go through that together. Today we're going to talk about I/O. Let me get caption. Any question before we start? Let me open this. And so we're going to look at chapter 8 today, which talks about I/O, and then we will work through the assignment for this unit. What I'll do for when we come back from spring break, I'll turn on the project, and then I'll give you a little bit of time as we will be in week 9, so you should have about 7 weeks to work on your project. We have to figure out our teams, as this class is going to require a team project. So I'll have the team sign up list ready. So we'll do that when we come back. So next week, there will not be courses, right? As we are going to go through spring break, and then we'll resume the following week. Okay? But if you have questions, you can shoot me emails, and then I can address that. Okay, so let's get started. As we mentioned, that we are going to go through chapter 8 today. We're going to work with I/O, or we'll talk about I/O. In LC3, when you use the directives, it actually handles this for you. In other languages, you have to kind of work with the register file, and we'll talk about that. So when you do in or put, what's happening with the display and also with the keyboard for the input. So input output is a component of von Neumann model, and it's very important. It is a way for us to bring data into the system and to be able to output from after we compute the data. So I/O is an essential area that we want to kind of think about. From my perspective in security, a lot of this has to do with I/O. For example, like you do see malware that is capitalizing on I/O, and some of it is written at the low level. For example, like rootkit is really something that was programmed to really take advantage of the vulnerability at the low level, right? Like some of it can be in storage like RAM, or some of it will be after the OSs. So in the case when you think about Trojan, it like a keylogger, it's really maximized its capability using I/O or input output. So This is a way that we would be able to look at how we can bring data into the system and then get the result after we process the data. So that way we can use it as humans, whether you're using the data from the application, or you're using the data for analysis, or you have some form of output there. And so when you input the data into the system, you have to find a way to store it. And so far, we've been talking about how we would use memory address and we can store that out to the location in the storage. Or in some cases, we would use temporary storage like our register. So input and output and storage, they always go together as we have to really allocate a storage to either temporarily or permanently store. And our input devices, as we touched on this before, but I want to review. Um, in most of our cases, when we work with the lab, we would see that when you interface with the user, you require some form of input via the keyboard. Now we use touchscreen as a way that we can also enter the data into the system. But things like motion detector, network interface, those are a form of input as well. And some of these, the network interface can also be output, and as it would be broadcasting to other system and so on. And then your output, you often see that when you display data on console, right? Like when we tell our system to multiply or divide and then output something on screen, that will be for the monitor to display. Or we can print out our data, and also your network interface, as I mentioned before, where it can take the communication and then forward it or send it to other system where it's going to output the result to other system as a broadcast or multicast. And then you have storage, which is going to be your disk, your memory. And then when you're looking at optical devices like CD-ROM, that's simply an output. But when you're looking at like burners, right, like a way that people can store data to disk, as optical device, like Blu-ray burner, DVD burner, those are legacy system, but then they work as both input and output. You can burn data onto a disk, and then you can also output from that particular disk. So to answer the question, the first question asks you, why is input and output important in computing? And going back to what the notes indicate and what we talked about, input output allows human to interface with the system. And in most cases, what you see today is that we have automated system that could be system interfacing with another system. In communication, we see this a lot. So when you visit a website, for example, right? A lot of the times, in order to transfer your data from your location to other location, you would see that you would have system interfacing with the system after it leaves your network. So you have automated routing system that will be forwarding the traffic. So in some cases, you might not have the human interface with the system, but the system communicating with other system itself. And so it would use your network interface, right? Or its network interface adapter to be able to communicate. Input allows the user or humans to enter the information into the system. And traditionally, we always wanted to do this to basically perform arithmetic calculation. Nowadays, we do it more in an advanced computation, right? Whether we're using it for VR, AR, or we're using it for gaming purposes. But when you're using your keyboard for gaming, you're inputting some kind of information into the system or commands. And then when you're outputting, you're really obtaining the result from the system after the information is processed. And so our system is really used to process the information so that way we can take that information for interpretation purposes or to do something useful with that information. So on the software level, we really have to think about how our data is entering the system and how it's leaving the system and what we're doing with that data, right? The objective behind IO as far as the program. Now, as you learn in the last or the prior lab, what you see is we normally take text and we need to find a way to decode and encode it. So whenever that you have an input as text, you have to make sure that you ASCII treat it. That means that we must convert it to something that the system would see as numerical value based on the input. And then before we output, we got to put it back so that way it would see it as text instead of a numerical value. And so part of your project is to be able to work with IO. Now at the higher level, you do see that there are libraries in C, Python, and other area. Like for example, right, you would include some library in C++ for C in, C out, right? And that's specifically emphasizing IO. So your compiler actually handles a lot of the low-level stuff that we normally see with ASCII conversion. When you use that library, it's able to take that library or the file and understand what kind of functionality that you want to include in your program for input and output. So when I do cin, right, it's basically on the low level, we would have that as in or get C. And then when you do cout, the compiler would treat that as a low level for puts or out. And so in the next part, what we'll do is we'll talk about some of the basics. So when you work with the low-level programming, you have to really see how the devices are using registers. And these registers is in charge of just a way to transfer your data between devices. So as it enters the system, for example, via the keyboard, it needs to put it onto a location when what we see, like as registers, before the processor is able to take whatever that's entered and be able to understand what's needed to be handled there. So there are two registers that are going to be at work. One is going to hold the status of the information, and the other register is actual data. Okay, so it's going to use the status to be able to track whether the data is entered or not. So the register is then mapped to a specific group of addresses. So again, we really refer back to memory. Registers are just a location or a region of memory that is used specifically for a certain purpose, which is in this case, input and output. And so then it is not like the other common locations where we would use it for just data storage. So it is dedicated specifically for IO registers. And so you often see it as memory mapped IO. Now, when you look at this diagram, you're going to see that there is going to be a control status register. So it's going to use that register to track to see the type of action that's needed for IO, for input or output or both. So the processor would then be able to tell the device what to do via, right, doing a write to the control register. So at the low level, you have to be able to use this register to make sure that the processor can communicate with the device itself. Even on, like, if you're looking at the USB level, right? How is the processor able to recognize the USB is to a driver, and it's just know and the processor know that that device is aware storing data onto it? The campus have a little bit of Wi-Fi issue today, so I just got dropped off, but let me pick up where we left off. Okay, so when you look at the way that the system is set up, right? When you have the control, that's going to be a write to the control register. Okay, so there's always going to be two register at work. One is going to be for the status, the other is going to be for data. The processor is then use the status register to check to see if the task is done. For example, if the user strike the keyboard to enter a character or to output on screen for I/O. So when you have the input of data, like I type into my keyboard when I'm prompted to enter a value, then that data is then transferred from my keyboard. And what the processor does is it's going to look at the register that's handling the status to really see that the task was done using the signal. And then it's going to communicate. So this is the way that it's going to be able to track to see if the device is sending signal or not. Okay. In the case of if we're outputting things on the monitor, it's doing the same thing. In order to output the data, it uses the control status register to check to see if the monitor is able to receive the data and output things, whether it's on console or on graphical user interface and so on. And then it's going to do the display. So this is the way that the CPU communicate with your electronic devices, which is the I/O. And so when you're outputting things on screen, right, things needs to be transferred from or converted to pixel. And all of that is going to be pulled from a certain storage location. So if we take a look at a game, for example, your GPU is at work and it has its own processor to really process the graphic side of the house and its own storage to be able to handle, right, the higher graphic application in the case if you're playing a 3D game. But on the lower end, if you're looking at that, all of that is really converting your bits that was stored into something that can be output on screen. So for the second part of this, we would say for question 2, it asks how many registers does a common I/O device have? Describe the purpose of the registers. So we know that there are 2 registers for the common I/O, like your monitor and keyboard. One is going to hold the data being transferred between the device and the processor, the computer. And the second register is to indicate status information about the device, whether it's ready or not. In the case where it's not ready, right, that status register is going to track it. So we always use 2 type of registers for our common I/O. And for question 3, it asks you how many device registers are identified, and we need to explain each type. We talked about memory mapped I/O. And so we know that these registers are mapped to a set of addresses that's allocated specifically for I/O device registers instead of other memory locations. So when we're looking at the memory array, not all of it is truly used for just data storage, right? We have specific location that's allocated for a certain purpose. And we have to understand this because in software development, we really look at how we're using space to store data and retrieve data. Any question? Okay. And as you look at 4 there, right, it talks about synchronous and asynchronous. So we'll move to that part next. And so here we want to kind of talk about memory map versus special instructions and how timing can impact how data is moved or accessed. So in the case when we're looking at I/O, and a lot of the times when you work with graphical user interface on the higher programming language, you would see that, it is event driven, right? In the case that you would have the system listening for a specific event. For example, if the user click a button, and that button is supposed to activate another frame with a pop-up window, for example, that is an event that occurs in that system. And on the low level, we do see that it is using a slower cycle from the CPU. So that gives us 2 areas that we look at for I/O. One is asynchronous, where the I/O is operating at a different speed, mostly slower than the microprocessor, and it is not in lockstep. So when you're looking at most of your devices, that will be asynchronous. For example, keyboard, mouse, and so on. Now, as I highlight here, most of your interaction, you would see that I/O is asynchronous. And simply the way I remember asynchronous is not together or equivalent. So we know that it uses slower cycles. And that means that it needs to require protocol. And protocol simply is a set of standards that is developed for a specific purpose. And it needs to have some form of handshaking or agreement mechanism. And when you see that, your data rate is going to be in a range, not in a specific static rate. So if the CPU has to synchronize with the device, then it doesn't miss the data or it would write it too quickly. And so when we look at the keyboard itself, it uses 1-bit status register. And that bit can either be on or off, right? 1 or 0. And this is what we considered as a flag. So for example, if you think about the electrical signal, it would then either receive the on bit, where it would receive mostly close to 5 volts. And then when it's not ready, it turns that off where it drops close to 0. So they simply use that status register to really indicate the bit for the flag to see, right, whether the character was received or not. So on the higher level, when you say cin and you prompt the user, please enter a character, right? And if the user types nothing, that flag or that register would then indicate that there was nothing received, right? Until the user strike a keyboard, then it would change the flag status so that way it would show that the user already typed. And it's simply that. It is just electronic signal. And the same way with the monitor, whether it is receiving some form of character to be shown or displayed. Now, on the synchronous level, which is different than asynchronous, your data that supply is going to be predictable. It is going to read and write at every specific cycle that is together. So it's using something similar, but this is called the ready bit. And this ready bit is used to synchronize the output for the characters that's used to either for input or output purposes. And as you know, that synchronous is going to be with the cycle. So when each time that the character is typed, for example, for the input from the keyboard, it's going to set the ready bit. And then as it reads, so I hope I can get through the session tonight. Okay, coming back. Sorry about this, but all right. So let's go back here and let me finish this thought, and then we'll answer the next question. And at sorry, we'll see how far we go tonight. All right. Okay. So if it detects a ready bit is set that the character is typed in, then it's going to be able to read. So it is a sequential process. So this ready bit is really used to set the sequential process for the processor to go and read, right? Without that set, it will not be able to read. Okay. And as you look at this right here, this is for some of the legacy, but then in the case where you would see the more modern processor, you would see that it would be a larger rate. Okay, so let's answer 4. Synchronous I/O devices usually operate at the speed that's different from the microprocessor, not in lockstep. We see that from the notes. Synchronous, so asynchronous, not the same speed. Synchronous data transfer operate at the same speed as the processor. It's using a fixed predictable rate for read and write at specific cycle. And keep in mind that your I/O devices mostly operate asynchronously. Okay? There are some devices that are operating synchronously, but most I/O devices operate asynchronously. And so with that, we can answer number 5. Describe the type of I/O control mechanism and how are they different or similar. So to control processing with asynchronous, that would require what we said was protocol or handshaking mechanism. And the reason why we really built out this in the industry is to make sure that it works across many different types of devices, right? So they standardize a set of rules that is used, and so that way it is applied. So it doesn't matter what brand that you use for your I/O. So you would see that there are many different type of mice and keyboards and monitors and things like that, because they are implemented and designed with specific set of protocols and handshaking mechanism. Doesn't matter what type of processor that you would use with these type of different brand IO, it still works the same way. And that's something that the industry come up with to make sure that we can integrate and have the flexibility options to use our IO devices the same way. Doesn't matter what brand and what company produce them. Okay. So it's a standardized process, and then going through and designing that and integrating it as solutions to make it more flexible for the consumer. And when we talked about how asynchronous um, control, that would be making it less predictable. That means that the CPU must synchronize the device so that it doesn't miss any data. Let me zoom out a little bit so that way everybody can see. And so if the data is not in a fixed rate, what will happen is it might miss the data. So synchronous is really designed for it to make sure that it sees all the data. Okay. That means that it is with the same cycle as the processor, or it could be writing too quickly, right? So we want to make sure that we synchronize with the clock cycle so that way it doesn't miss any data. So that means that it operates in both, right? Synchronously and asynchronously. Some cases it would use asynchronous, and in other cases it would use synchronous. Any question? Okay, so we talked about I/O control mechanism. So how does it know, right? And this comes back to what you actually use on a daily basis. Okay. When you open an application and things are showing up on screen, like Microsoft Word, for example, right? At one point, you are going to have to type in something on the document, or even when you open your browser, right? That talks to your network adapter, whether it's wireless or the network interface card. So the processor goes through these mechanism. One is it's doing polling. That means that when it polls, it's actually checking on the device. Okay. It would go and find out, is it ready? Is it ready? Right? Or in the case that if the device needs attention, so for example, right, the device can generate an interrupt. Think of an analogy for this is like the processor is the teacher, right? And the teacher, when it does the poll, it checks on all the students. Are all the students available? Are all the students ready? But when you're looking at interrupt is a way that the device can get the processor attention. In the case where it needs to get that attention, it's like a student raising its hand, right? So it generates an interrupt to let the CPU know that, hey, I need your attention and I need you to process this. So interrupt can be in many different forms, right? And in your operating system, you normally see this, they use a value to indicate a specific interrupt for a specific device. So for example, it will be like a number 1. And whenever the processor sees that interrupt, it knows exactly which device needs its attention. In the case of polling, it's going to check on the devices and it's going to see the status of the devices, whether it's ready or not. So that means that it constantly have to look at the register to see if the data is arriving or if the next data is there, right? And the example that the book give is like, are we there yet? Are we there yet, right? So it's going to check up on all the devices by looking at the status register. And for the interrupt, the device send a signal. And this is in the form of electrical signal, but on the operating system level, we see this as an IO interrupt value. Traditionally, if you're looking at the old operating system, like the old Windows, right, you can manually set this. But in the case where if you have conflict in the signal, let's say that I have 2 devices that have using the same numerical value, it creates an issue, right? So now when they're designing the operating system, they actually use, right, they don't allow you to control that. It automatically assigns specific value for a certain signal. So the keyboard would use specific value, the monitor would use a specific value, and it would raise the attention to the processor by generating that signal. So that means that it would say, hey, I'm ready, pay attention to me, and perform the task for me, right? So coming back to assembly, right? In LC3, we don't specifically program this. We use directive or pseudo instructions to handle a lot of this. But other languages, you can work directly with the IO registers. So that means that it's using specific opcode, and you see this with the pseudo instruction. And you are, when in that case, when you're using that opcode, it actually use the registers that's assigned to that specific input and output for the operation using specific instruction, hence our directives. Okay. So when you hear the term directive, a lot of that is really referring to system task. And when you deal with system tasks at the low level, that's really talking to the hardware. And so in that case, you're going to see something like this. Okay. Where it dedicate a certain bit size to really assign to a particular device. So it can distinguish between a keyboard and a monitor. And then it would dedicate certain bits for flag and then the operation for that device. Like, register an input of a character or be able to translate and output that character as text. So when we look at the memory address mapping, how we see each of the device registers, simply it is a dedicated address that is used for that I/O. And in assembly, when you read and write, that's a load and store. And that's how we're able to get data transfer. Just like what we've been doing, right? We load to a certain address, and then, or we load from a certain address and we store to a certain address. And so what is that address then? For the keyboard, it is specifically at this location, and this is for LC3, right? So when you use other language, you just simply look at the documentation and they would refer to specific region of that address. So the engineers, they already designed the processor to understand that that's the area for, mouse, keyboard, display for the I/O. So for LC3, your status register is at FE00. This is where it's going to go to check for the status if it receives the new character or not. Then for the data itself, it is two location later. So you have FE02. This is just for data. And you would have this storage for the character. So when you issue a get fee, right, in your program, and you prompt the user to enter, this is being used. These location. One to check the status, the other for the data itself. And then when you do an out or a put, right, it uses the subsequent location. So for the display, it's at FE04. That's the status. It's going to go here to check to see if the monitor is ready to display on screen, hence the console, right? And then what is being displayed is from the subsequent address 06, FE06. Make sure we know these for quiz and final exam. Okay, so let's move to the next one. For number 6, the location for the keyboard registers, right? We talked about FE00 for the keyboard status register, your KBSR. So the status is always going to come before the data. And then FE02 for the keyboard data register, your KBDR. And then for your display monitor register, it's that the subsequent locations, so just remember it's incrementing by 2. So as each is going to be a word. So FE04 and FE06. So the 04 is for the DSR and 06 is for the data, the DDR. Any question? And so if you reflect back to like C++, right? When you type your variable like char, let's say char input 1, right? You actually section that container at a certain size. And so that reflect back to what you see as data storage, right, for the input. So the compiler, when it compile your program, it push that on stack, it uses a memory location on stack. but it's going to have to retrieve the input from another location in the memory where the keyboard is used as registers to bring in the data. So when you do a CIN, right, it's going to use these register to check whether the data is ready, get the data into the system, right? Get it to the location where the compiler see it for storage. And most of the time we point to it, right? We transfer it or we point to it. So it gets to that stack location, use that data to operate, compute, and then before it output, it's going to take it from that region of memory from the stack, push it off, and then transfer it to the DDR and the DSR for display when you do a cout. So in this class, what we see is we see the mechanism and what's being used from a higher level to the lower level. Any question? Okay, so we will revisit some of this when we talked about polling and interrupt later on. Here it gives you some additional information, kind of reflect back to the table with the addresses. And then this is the example for the input. So when you're looking at the ready bit, that one is at location 15, your bit 15, it's at the beginning. That's how it's going to check for the KBSR. And then your data, the data itself is going to be 8-bit here. So when you do like the character input, it's whatever that character is, it's going to come in as numerical value. It stores it here, right? And then we ASCII treat it. So the ready bit is in the front for the KBSR, and then for the KBDR, it's going to be bit 7 to bit 0. That's the 8 bits in the back. So when you write this at the low level, right, there's no magic to it. We still use load and store. We have to use a label, and then you fill it with the right address. So how do they write this for the keyboard and the monitor? Is like this. You have the pointer, which is the location of your status and your data. You go and you read it from register 0 because that's where the data enters, right? And then you check, you load it to the address for the status. Then you loop it back because we have to go to the next address for the data itself. So you're going to load from register 0 to the data pointer. So if the character is not entered, it's not going to check true here. So you have to apply the condition where it's going to check, right? Is that signal there or is it not, right? So we have to do a 0 positive here. Okay. Any question? And so some of the logic you would see, and this is how the rest, right? If you're interested in looking at how the gates would be integrating with the memory. So your address logic controller, before it accesses it from the memory address register, it's gonna use that to really reference the address, and how it reads it, it has to look at the logic here. So here they use a multiplexer or a mux to be able to handle multiple logic controller. And with that, because we need to check it for 0 positive, it needs to apply the multiplexer. So those are the combinational gates that's used to be able to access the data. If it's there, right, go and retrieve the data. If it's not, right, then just wait. So that's how it's able to see using the address control logic with the multiplexer. And so here we see that it's using your keyboard and your mouse, and then simply it is a poll on both. Is the keyboard ready? If it is, right, get data. Is the monitor ready? If it is, send data. If it's not, just wait, right? So it applied the conditional operations, and then we simply fill it with the address. So once you understand how to write, right, assembly in other areas, it is the same basic components that you would see for I/O, similar to what you would see with like I/O libraries, where on the higher level. So when you do include I/O, right, basically it is a library that you use, and on the low level, it interpreted as assembly like this. Okay, so explain the functionality of KBSR and KBDR. So for the keyboard register, we know that 1 bit is used for the status flag. That's the first bit on the most significant bit, which is bit 16 on a word. That is either on or off, and that's going to check to see if your keyboard is ready or not. So when I strike a button, a character on my keyboard, right, it activates that signal, and it is at bit 15. And so if it is ready, then it's going to go to the KBDR location, and it's going to go to the 8 bits, bit 7 to 0, where it's going to see that character that I typed. And then for 9, the functionality for the monitor, similar. We have the DSR that's also at bit 15. This is going to be used to check the signal if the monitor is ready or not, your ready bit. And then if it is ready, then it's going to go to the DDR, bit 0 to 7 or 7 to 0. And that's what's going to be used for display, which is the data. So when you do an out or a C out, that's what happens. So in the next part, we're going to talk about like what is the priority, right? Because a lot of times you do see some devices that, it does compete for priority. There's priority level in specific devices. And then there's some devices, it will queue based on the next level priority. And a lot of this is really now being handled by the operating system side. Okay. So let's talk about that next. And then we touch on this just now. So let's talk about polling and interrupt a little bit more and talk about priority here. So we know that for your external device, it can force execution to stop. That's a halt. And your processor can satisfy the device need. So it would generate that interrupt to stop. And so a good example for this is, let's say that I am displaying a scene from a game, and I'm having some issues, right? Like maybe it's just slow, or it's not transitioning well, or it's not showing what I need it to show. And from the operating system side, from a Windows PC standpoint, you can use your combination keys like Control Alt Delete to stop the process, right? And in other area, that's a kill process. So my monitor is actually displaying the scene from the game. But when you press Control Alt Delete on your keyboard actually generate an interrupt and it overwrites whatever the monitor was doing, right? So it jumps up on the level of priority. What it does is say, hey, I need the processor attention because the user just typed these keys and it's generating a kill process for the monitor. So it's gonna stop whatever that it's doing to display, and it's gonna take you to the task manager. So it's transitioning. So the monitor is still displaying something else, but the keyboard actually generate interrupt at that point. Okay. So you can force certain execution program to stop and then certain device to take it off of the priority list or lower it in the queue level. So that means that the processor has to satisfy that interrupt request at that point in time. And then in some cases, it actually resume from wherever that it stopped, the stopping point, as if nothing happened. So it will continue in that same, so it's gonna, once it fulfill the interrupt, then it's gonna pick up. Okay. And you see this happening with other areas as well. So now comparing interrupt and polling, when you poll a lot, it's gonna consume a lot of power and a lot of resources. So your power cycles and it needs to check, right? So think about it like if you're a parent and you have to constantly checking on the kids, then it's a lot of energy that you have to put to that, right? The amount of the frequency that we have to really pull through. And so the example of this is that it's going to collect the current input and it's checking against what was previously done. And as we talked about interrupt before, it is really a way to generate a signal for the CPU to see that it is an event that's occurring. And so your text indicated that the CPU can use this we can test it by generating the interrupt signal or set it. And that will move it up on the higher priority list. So whenever you have an interrupt, right, it moves that event for that device higher up in the priority list. And so in that case, you see that the bit 14 is then activated right next to the ready bit. So when it sees that turns on, then it knows that the interrupt is generated. And that's how it works. Okay, your interrupt is signal. Okay, so then for number 10, it asks you to describe how the CPU handle the priority for the IO device. So in the case where we're using polling, which it does, it checks on the status register until the data arrives, or if the device is ready for the next data. And it keeps checking for that specific bit, which is bit 15. So if it's ready, then that's 1, right? When it's 0, then it's waiting. But in the case where the device needs attention when it generates an interrupt, which is bit 14 next to the ready bit, it will activate that bit, which sends a signal to the CPU that pay attention to me, I have data. Any question? Okay. And you notice that they're using, it shows with the AND gate here, right? because you can see 1 and 1 or 1 and 0, right? The outcome of that with the logic. So these two bits are working together. One is for the status, the other one is for the interrupt. And so in LC3, we treat this with the 8 priority level. You would see the PL 0 through 7. So there is higher priority based on the device and also whether it generates an interrupt or not. So your encoder really is used to select which one is higher. And that's going to compare to the current priority level. So when it generates the interrupt signal, it moves up in the level. Okay. And so with that, what you see is that if it's not set, then it's going to keep going with the next instruction where it's going to handle the next level priority. When it's set, it's going to transfer that interrupt service routine to that current level. So it moves it up in the level. So it's going to handle that service routine. And whenever you see this, it's a system function. A lot of your commands is actually being handled with the service routine. So when we generate the interrupt or the device generate the interrupt, it's going to transfer the control, and it's simply checking that 14th bit or bit 14 to be able to see that. Okay. And so this is what you see with the fetch decode. Is that bit on or off? And if it is yes, it's going to transfer it to the ISR, and then it's going to do fetch decode and all of that at the low level. So it is still the programming process here that you see, right, for execution. So when we think about this, how we'll be able to implement it in our code. And then this is the memory mapping. Okay. So this is a fairly short chapter. We just basically work with 2 IO for LC3, right? One is for input, one is for output. In the case where if you use assembly to write firmware driver, you will have to work with other form of IO. And even on the higher level, you would see that we integrate libraries that is already in existence to be able to adapt it for specific devices. And so you see a lot of most application work on the low level. So if you tell me, oh, I want to write a mobile app, right? The mobile app itself uses a lot of IO. For example, like to activate the app, you touched your screen on your mobile device and it opens up a certain screen. So if on the UI level, you already see that with the IO integration. And then also, from the back end, there's a lot of IO at work. But in this class, I really want you to see what the processor sees as far as IO and how it's using IO. With the register to really handle like how data is being accessed or transferred from the device to it. Okay. All right. So if you didn't catch that at the beginning, I will activate your project after spring break. We don't have class next week as we are going through spring break. And then for this week, we're just going to do the assignment and lab. I took off the homework assignment that I originally assigned in this class. It's just a quiz review. So we'll use the game to kind of prepare for our quiz when we come back from spring break. I took it off because I want you to have a relaxing spring break. And then when you come back, you're ready to tack on the last, few chapters that we're going to go through, work on your project, and then prepare for your final exam. So we are at midpoint, and I don't do midterm. I use the project as an assessment tool for this class with the final exam, along with your assignment quizzes. So I'm going to stop recording. We end the session for the lecture. I'll stick around for questions.